Okay, last week of this semester. So the last week, the class materials will not be in the final exam, anything. So just relax. So today we are going to talk about the gap between this course and also the state-of-art research in the general. Sorry about that. In the general software and system security. So I used to offer a class called Advanced Software Security to bridge the gap between what you learn in this class and the research. Well, of course, that course itself cannot bridge the gap, but can give you, move you a little bit further into that direction. So, so what I'm going to do is I'm trying to pack what I offer in that class, the course, the semester course, into this class to give you some basic ideas. What is the most important topics in advanced software security and how we can use them to do research. So in particular, we will talk about 4 areas. The first one is static analysis, the second one fuzzing, dynamic taint analysis, and also symbolic execution. So some of the terms, maybe you heard of them before. For example, static analysis, I mean, if you took compiler classes, principle of programming language courses, you heard about that all the time. Fuzzing, that's kind of like a buzzword. It's been super hot in the last decade. So probably you heard a lot of fuzzing tools. You have been using some fuzzing tools. But dynamic taint analysis and symbolic execution, probably most of you haven't heard of that before, but they have been widely used in the last 15 to 10, 20 years in research for security research. So static analysis, well, if you want to enter the security research, you will use some kind of static analysis. And in academia, the tool usually we use for that, there are all kinds of tools. And one of the most widely used is just the Llvm. So Llvm is just a compiler, right? So it's an open source compiler developed in UIUC probably 15 years ago, 18 years ago. So the guy who developed that, I think he was a PhD student. So he left. I don't remember if he got his PhD, but anyway, he has been working on many other interesting projects. If you just Google Llvm, who developed that, I think his last affiliation was with Apple, I think. So Llvm is one of the, so starting at the university, now Llvm is one of the most used compiler collections. So it used to be GCC, but now more and more people are using Llvm. And also in our lab, a lot of our research, when we implement something, we implement on Llvm because it's just almost impossible to implement on GCC. If you want to change GCC, that's very, very difficult. If you change Llvm, it's much more friendly. So Llvm, they define their own intermediate language or intermediate representation that is called IR. So when you have a C code, we have Java code, you have other code. That code was first compiled into one language. A language is called Llvm IR. Then the Llvm IR will go through all kinds of optimizations, goes through all kinds of analysis. So usually what we work on is we develop Llvm process that to analyze the IR, to find the vulnerabilities, and that's one thing. Also to change the IR to inject some new protections. Then the IR will be compiled into the eventually machine code. So this is one of the, I think there were several papers. This is one of the original papers on Llvm. Oh yeah, that guy's name is Chris Nantner. Yeah, he was a student at UIUC. and that's the professor's name. The professor is still with UIUC. So it was published in Code Generation and Optimization Conference, one of the good conferences in compiler. So Llvm, a compilation framework for long-time program analysis and transformation. So when they started the project, Llvm short for low-end virtual machine. That was the name before. But right now, I don't think they still say the full name is low-end virtual machine. Well, anyway, this name is a little bit confusing, right? For most people, virtual machine doesn't really mean compiler, but there are language-based virtual machine. I believe that's what they mean. Anyway, so right now, Llvm is just Llvm. It doesn't short for anything anymore because the name is a little bit confusing. It's a little bit narrowed. Doesn't reflect the whole picture of Llvm anymore. So the whole thing is beautifully written in C++. Use not of a standard template library. If you program in C++, you know, using those libraries is not an easy job. It's quite complicated to understand how the library works. Heavily use the vector set or the map, those kind of things in STL. It's an open source project. It's divided into many smaller projects. If you want to learn this, they have an official website. Let me explain a little bit why Llvm is so special. So this is a typical compiler overflow before Llvm. So there is a front end to translate whatever language you have, to do lexical analysis, syntactical analysis, then generate some kind of intermediate language, abstract syntax tree. Then there will be an optimizer to optimize the code, to do analysis, to find some errors in the code. Then there will be the back end to generate two different machine code. The same C code can be generated into x86 machine code, ARM machine code, and now if you can even compile C or C++ code into VHDL, then generate bit stream, and you can directly program FPGA devices, right? So directly program hardware. So one of my PhD students is actually working on the security of those things. Then each C file can be compiled into a .o file for those machine code architectures. Then a linker can link them together, link to an executable. So this is a picture I showed all of you in the very first class or second class, right? So, and the example I'm using here, they are actually all GCC examples. So this is a C code. Then you can use part of GCC called the CPP to program this code. But actually, you can also use, you don't have to use the command CPP to do that. You can just use the command GCC to do that, because GCC is the driver that has everything. Then remember, you compile the C code into .I code. So this part is not really compiling. This one is pre-processing. Then compile into .s file. That's assembly file, right? So for Llvm, we're not going to generate this .s file. Instead, we're going to get the intermediate, its own IR. But for GCC on x86, we're going to get a .s. Then we're using assembly to generate the machine code, linking them together to this. So the main contribution of Llvm include many things. One of the most important one is that Llvm IR, okay, intermediate representation, its own language, or we can also call it Llvm bitcode. So the front end, if the front end is, if you are using C or C++ as the input language, then the front end is a tool called Clang. So Clang will compile your C++ code into the Llvm bitcode, or IR, then all the optimization will be on the IR. So you can use many different the front end. So we have a well-defined interface. The interface is the Llvm IR. You can use different front end to compile all kinds of language you want to use, but they will be all compiled into the same IR. Then at the IR level, we can use the same optimization code. We can reuse that. We don't have to redefine the optimization, re-implement the optimization for different languages, because they are all the same language. They are all in the IR. Then after that, you will just use another backend to compile into whatever architecture you want to use. You can do ARM, you can do x86, other machines, and also, like I said, you can even do VxDL or WebAssembly. So WebAssembly is also quite interesting. It's kind of some kind of bytecode you can run in your browser, but kind of like assembly, very fast. One of our professors, Professor Llvm, she's working on WebAssembly, a lot of security issues on WebAssembly. Then, if necessary, you can still link things together. So this is a Llvm workflow. It's similar to the previous compiler, but the difference is this part. So previous compilers, they usually do not have a well-defined this intermediate language layer, which means their optimization has to be done for different languages. When you develop a C compiler, optimization specifically right for that C. You develop a Java compiler, then optimization specifically implemented for the Java part. But the principles for optimization, they are the same, so they can be implemented together. Okay, so this is what we have right now. We have many different front end for different languages. For C, we have Clang. For Haskell, we have this front end, even some Llvm GCC front end. But anyway, they were generated the same Llvm. Then the optimizer part, they have a collection of all kinds of optimizers, and that's usually what we also develop. Because optimizer doesn't necessarily optimize the code. You can define an optimizer to analyze the code. Just analyze the code at the IR layer. You can also develop optimizers to change the code. Well, as long as change the code is kind of an optimizer. Imagine the stack cookies we started before. So those kind of programs, if we want to use the stack cookies, we insert a piece of code to push the stack cookies on the stack at the beginning of the function, and also at the end of the function, we insert some cookie checks, right? So at a C code level, we're not changing the C code. The developer will not going to write that piece of program. We're not inserting in their C code. So what security guys do is we change the optimizer, we change the compiler part. Give me any C code, then I analyze all the functions. And I decided this function I want to do the cookie check. So I insert those instructions at the beginning of the function and insert those instructions at the end of the function. So that's usually what MyNav do for some other projects. We mainly work on ARM architecture. So the backend, we have all kinds of machine architecture as well. So Clang is one of the, I think Clang is part of the Llvm. It's a C frontend, C and C++ frontend. Okay, let's take a quick look at the instruction set of that intermediate language, what it looks like. So first of all, that instruction set, that language itself, it's kind of like, you can imagine, it's kind of like an assembly language. It's an assembly language to its own virtual machine, Llvm virtual machine. So it's a RISC-like instruction, kind of like ARM instruction. So not very much like x86 instruction. x86 is complex instruction set, but risk is reduced instruction set. There are 3 addresses for those instructions. It has the explicit control flow. There are unlimited numbers of virtual registers in that language. And all instructions will use this thing called the Semantic Single Assignment Form, SSA. So this is quite important in the program analysis and also compiler area. If we change a program into the SSA form, then analysis on them will be much simpler. Without that, it's very complicated it's something almost impossible to analyze. So I will show you one example. What does it mean? So the static single assignment form means any variable in the programming language will only be assigned once. Okay, for example, this could be a C code. So y is a variable. We first assign the number of value 1, then we assign it the same variable value 2. The x assigned with the value of 1. So in this case, this is kind of like all of our high-level programming language. The variable y was assigned the value twice, okay? So because of this, a lot of program analysis on this language will be very difficult, very, very complicated. The algorithm get too complicated, sometimes cannot get it right. So then scientists find out if we translate this program into a different form, let's say y1, so y was assigned twice, and we're not going to do that. We're going to assign a different variable to y. So y1 is assigned to 1, y2 assigned to 2, and x1 will be assigned or y2. So x1 were never assigned as y1, right? So you can see from this one, even by looking at this, we know x1 has nothing to do with y1. But when we look at this piece of code, it's not that clear. X has nothing to do with the first y assignment, right? So so all Llvm, it will look like something like this. Every variable will only be assigned once, and that is called a static single assignment form. So Llvm IR, well, there is a human readable text format. There is also a bitcode format. They are basically equivalent. You can directly run them in Llvm virtual machines. Okay, so the SSA static single assignment form was first proposed in 1988. Has been a long time ago, and it was also one of the top conferences. The best conference in programming language, POPL, Principles of Programming Language. There's another programming language conference. Those two are the best. Another one called PLDI, I believe, Programming Language Design and Implementation. So those are the two leading conferences in programming language. So for most people, we're not trying to improve Llvm. We're not really programming language guys. For people like me, we're security guys. We use Llvm. So when we use this Llvm, we usually develop something called Llvm parsers. So that is something get called when in the Llvm optimizer part. So Llvm provides very good interfaces for us to use. For example, we can develop something called a module pass. So a module at a C level, one module is just a C file. Then there is a call graph pass, can traverse a program call graph, and function pass, basic block pass, and many other passes. And you can imagine if we want to implement something like a stack cookie check, that stack cookie check should be at every function, right? At every function, we are going to insert that push to stack and check the cookie. So what we are going to develop is just a function class. And the function class, we can first, so it will go through each function, then decide if for that function, if we want to add that. And also, like I said, we can develop two kinds of passes. One is called analysis pass, another is transform pass. Analysis pass is passes you are not going to change the IR. You are only collecting information, but transform passes, you are going to change the program. So that stack cookie pass, obviously it's a transform pass. You're going to insert instructions there. And the instruction you insert, you don't have to insert the machine instructions. You insert instructions also at the Llvm IR level. Then after it's compiled into different architectures, it will be different instructions. So you do not need to develop the stack cookies for different architectures. Like I said, module is just kind of like a C file. So a module has functions, has global variables, and a function will have basic blocks. Inside basic blocks, we will have different instructions instructions. Here, the instruction we're talking about Llvm level IR instructions. Okay, so that's all about the Llvm part and the static analysis. So if in the future you have a chance to do security research, especially at the program language level, sooner or later you will use Llvm. The next topic we want to talk about is something called fuzzing. So in this course, we have been manually inspect the source code and sometimes binary code, like the CTF. The midterm, you are actually analyzing the binary code, right? So you inspect those code to see if you can find some vulnerabilities in those code and try to exploit that. And then obviously, the goal here, especially as researchers, we're trying to automate those steps. We try to say how we can, give me a piece of code, either source code or binary code. Then I develop an algorithm, I develop a tool to automatically tell you if there are bugs, or even we can automatically exploit those bugs. So we don't have to do everything byte by byte by ourselves, right? So one thing is static program analyzer, kind of like the compiler, kind of like the Llvm. We develop passes to analyze the code and try to find those vulnerabilities before the tool is shipped, the product is shipped. Another thing is the attacker. So usually those ones, people doing that are not necessarily attackers, right? They could be developers. They want to fix the bugs before the product is shipped. Then there are also attackers, also developers. They want to find the program vulnerabilities bugs after the program is shipped. Fuzzing is an approach to do that. So fuzzing basically means we run this program. So in those static analysis, when you do Llvm, you're not really running the target program. You're analyzing the target program. The compiler is running. The analyzer is running. So in fuzzing, we run the target program, and we feed the program with all kinds of different input. So if I can imagine you are doing the CTFs, right? You run the program, you give it different input, and say if it crashes. Fuzzing is the same thing, but it does that at a much faster speed. It may try millions of different input in hours. When you do that manually, you try several different input in a minute. Fuzzing can try hundreds of that, thousands of that in a minute, and try to crash the program. So obviously, fuzzing is more effective when applying to standalone applications. And the good thing about fuzzing is it doesn't generate false alarms. If it generates an input and the input crash a program, it means the program will crash for that input. Of course, some program is also not purely deterministic. The program itself has some randomness, and sometimes a multi-thread since they're complicated. But if the program crash means at that point, those input will crash a program. Then obviously there is a bug. But a bug doesn't necessarily mean it's exploitable, right? But here we're only talking about finding a bug, not really exploiting a bug. So let's say there are two types of vulnerabilities. One is known vulnerabilities. Someone already find the vulnerability, and we want to say if our code has the same vulnerability, or there are unknown vulnerabilities. No one knows that before. And also we have static approaches and dynamic approaches. So fuzzing is a good tool to find unknown vulnerabilities and using a dynamic approach. Static analysis also can find unknown vulnerabilities, but it's more like using a static approach. Okay, everything can be fast. Fuzzing is just to give different input to a program. So as long as your program takes an input, it can be fast. Let's say you have a autonomous car. Autonomous car has a lot of input. It has a LiDAR. It has maybe has a radar. It has GPS. It has some of them even have a camera based, right? Then you can fuzz the camera input. You can fuzz other sensor input, LiDAR input, everything. Many of you use Windows, so you use Word, right? So Word opens something like a Word document. The Word document can be fast, right? A lot of programs I showed you in this class, we use stdin as input. Then you can fuzz the stdin. So I give you some video here. You can also take a look. So let's say, what is generic architecture for fuzzing is, let's say we have an application. Then first we need to run that application. That's a target application. We want to find the vulnerability of it, or we want to exploit that. That application will take some input. Let's in this case say the input is just a read system call. It will read from stdin or whatever places. Then our fuzzer will basically do two things. The first thing is our fuzzer will generate random input. Of course, how to generate that random input can be very scientific. How do we smartly generate that? So we do not generate many input, but it can crash the program faster. So there is a input generation algorithm, generate different inputs and feed that input to the program. That's the first algorithm. The second algorithm is we just need to find out if the program crashes automatically. Okay, so the second algorithm is just to try to find out if the target program crashes. And sometimes it could be very high level, just crash or not. And in other cases, it could be much more fine-grained. Okay, if it crash, why it crash? Right? Because of this memory, because of you read this file, it crashed. And you can imagine those information can be used to guide us to generate input more efficiently, right? But there are other algorithms right now can be designed for those fuzzing tools to make fuzzing much more faster. For example, create a process. Sounds like very simple. You just create a process. But that process creation in reality could be very slow. Create a new process on Linux is quite slow, right? If the program is big, it will be slower. And it may become the bottleneck there. If you want to fuzz millions of inputs there, that may become the bottleneck. So how do you speed up the process creation? Or you don't even create the process, you fork it somehow, right? So that is also of great importance, just to fast forward. And also, after you generate all kinds of input, how do you manage the test cases, those inputs, so you can better come up with new test cases, just like what I said before. Okay, and fuzzing after 10-15 years of development, also there are becomes like 3 types of fuzzing. One is black box fuzzing. Black box fuzzing, kind of like in the CTF, you just try different inputs to crash a program. You haven't tried to understand the program yet. You just give it different input and say if it crashes. If it crashes, what does it say? To give you some information. So black box fuzzing treats the target program as a black box. Then there are grammar-based fuzzing. So the input, we are going to define some rule there to help us generate a new input. And also there are white box fuzzing. This is also related to other techniques. So white box fuzzing basically means we know the program. We know when it crashes what exactly happened there. We can identify it crashes because this branch, it entered this branch and eventually it crashed. So it can help us to, next time we maybe generate more input for this branch or for different branch. So we can cover, think of program as a control flow graph, like a tree structure. One goal here is to cover more nodes in the structure. If you cover more nodes, you test more cases, then more likely you are going to find bugs. If you are always just testing one pass and the whole other nodes of the tree was never tested, then you're not going to find the other bugs in other areas of the tree, right? So also right now, people we are at the stage of like the 4th generation of fuzzing. The 1st generation is like early 20s, early 2000s, and before that, people have this concept has been there. But I believe when I started doing my PhD in 2009, fuzzing was still not very popular at that time. Fuzzing was getting very popular in the last decade, I would say. 2009, I don't remember many papers on fuzzing, but now all the big conferences, you can see a lot of fuzzing papers. They're fuzzing everything, fuzzing cars, fuzzing all kinds of software, industrial control system software, your regular Linux kernel, your Android phone. People are fuzzing everything right now. Not only fuzzing the software, fuzzing protocols as well. They change the protocol field to say if the software can handle that, and maybe sometimes it's a protocol design problem. Sometimes it's a software implementation problem. The 2nd generation is something called the coverage-based fuzzing. It's what I described to you just now. It's like you understand the program, you see the control flow graph of the program. You're trying to cover more passes of the control flow graph. That's coverage-based fuzzing. And one of the popular tools is called AFL. This is also an open source tool To use this tool, you need the source code. The target program here, we need a source code. Some of the fuzzing, we don't need source code. Then right now we're in the fourth generation. We use something called a symbolic execution to help fuzzing. I will explain this later. Let's take AFL as an example. AFL is one of the most popular tools. A lot of people have been porting AFL to different architecture to fuzz different things. AFL, we just use the fork system call to speed up the. I think AFL was developed on top of Llvm, I believe. I think so. So anyway, to use AFL, you need the target program source code. Then AFL is going to instrument that source code to change that source code. For example, that program will never fork. Then, but however, if you do not fork, then you want to create multiple programs, then you need to kind of the OS level, create the program multiple times, right? That will be slow. So instead, I will create a fork. I will directly insert a fork in the program. The fork will fork different copies of the program, so it will be much faster. Fork is fast because it's just a simple copy. But create a new process will be much slower. Also, you just use Unix signal to observe if the program crash or have other things. So you will use some heuristics to generate input. So try to use smaller number of input to crash the program. This is developed by an employee at Google. So I mean, you know, all those tools you can find who is the author. You can even follow those authors on Twitter, because most of the technology guys are on Twitter talking about their work. Let's say, what does coverage-based fuzzing mean here? So let's say this is a source code. You can see that the source code is, this is a function, for example, and the example takes a string. And let's say here there is a bug. There is a programmer crash. Somehow there is a bug. But the bug is deeply embedded here. Only if the first three characters matches some letters, we will trigger the bug. So a lot of real-world bugs will be like that, deeply embedded here. So how can we actually trigger this? So a coverage-based fuzzing will generate a control flow graph like this. Then you will try to reach every node in the control flow graph. So that will be better coverage. Of course, even if you reached every node, doesn't mean you will always find the bug. Maybe there are some other conditions, but that give you a higher chance to find the bug. And in coverage-based fuzzing, one of the metrics to say if your tool is good is to say how much of the control graph your tool can cover. Okay, so that is our second topic, fuzzing. The third one is something called dynamic taint analysis. As you can see, this one is also a dynamic approach. It's called a taint analysis. When we say dynamic approach, it means we're going to run the program, the target program. When we say it's a static analysis, means we're only analyzing this program, not running it. So in dynamic taint analysis, we track the information flow through a program at runtime between some sources and sinks, and try to find vulnerabilities. And it can be used to identify some unknown vulnerabilities, especially for vulnerabilities that can only be triggered by user input. For example, you have Android applications, you have iPhone applications. How do you know if your Android or iPhone applications, whether they are leaking your sensitive information? One way to do that is you can taint your sensitive information. Let's say sensitive information here is your credit card information, which is stored on your phone. You taint that information with a color. Then that will be the source. Then you execute the program, and eventually to say if the sync could be a network function, is sending out a package, or write something to a file system, that is a sync. You can check at that point if the input to that point is also tainted. If it is tainted, then it means your data is leaked. But what is good about this is, let's say there is a malware. The malware will first try to retrieve your credit card information, then encrypt your credit card information, then send that out. So imagine you have something like a sniffer, like a Wireshark, right? If you develop a network-based system on Wireshark to analyze all the packets from your system going out, and say if any app is stealing your credit card information, you will not be able to catch that because your credit card information is encrypted. You will never be able to catch that. But if you have a taint analysis system, you will see that even though the data is encrypted, you do not see the content, you see it is tainted with a color, and it's sensitive information. I'm not sure I'm going to explain this. Let's say, so there is a great paper published also 15 years ago, maybe 10 years ago. So they formalized the taint analysis like any other programming language paper. When you formalize something, you first define, how many of you recall what this is? This is basically the syntax. Right? What is this called? This is called the BNF, right? In your programming language course, the BNF defines the syntax of program, right? So let's say the program can be multiple statements, that's the meaning. And a statement can be a variable assignment, can be a store function, can be a go to, assert, that's the meaning of it, and can be a if, go to, else. Then the assignment could be a variable assigned by the expression, and the expression can be a load, can be different things, and there are different operations, and there's a value is a 32-bit integer. So this only defines the syntax, that's the BNF. Then, besides the syntax, we also need to define what is the meaning of the program. So when you develop a compiler, your compiler code defines what is the meaning of the program. Give you a piece of C code, you generate corresponding machine code. Then by doing that, you are defining what that C code means, because you are really generating machine code, and machine code does the concrete things. But that's kind of like the natural language for machines. Okay, it cannot be reasoned. It's difficult to understand. That's why we have something called operational semantics, to using a more formal math-like language to define the meaning of each operation or instruction. So how many of you heard of this before? Operational semantics? No? Okay. So I believe if you took the compiler classes, this will be discussed. So in operational semantics, we have a operation here, a computation, or it could be an instruction. Then we define what does this instruction mean. Define means we say before this instruction, this is a state of the computer. The register state, the memory state, all the state we can define. Then after executing this statement, the computer will end up in the end state. And what will be the next instruction to execute? So this clearly, in a formal language, defines language. For example, in the language we saw before, we have input, we have variables, we have different condition stores, and this operational semantics defines that. We just take let's use an easy one example. It's the input. So input is an operation, means we are taking V from input from source. Then what happens is basically nothing happens. We're just getting from it. So this, let's say another example, like store. Okay. So there is a store instruction, store E1, E2. The first E1 may be the expression for the address, E2 may be the value, I say. So before that, we define that the current state is this and this, and we're going to execute this. Then what happens is value 2. So E2 will evaluate to value 2. E1 will be evaluated to value 1. It looks like those two are E1, E2 in these cases are both addresses, I guess. Let's say store. Do we have store? We don't have. Okay. So anyway, you can say, let's say mu is a memory. So what will be memory will be updated. So V2 will be updated to V1. So that's a store. Yeah, we don't have to go too deep to this. Because our goal is to, well, one good thing about this is this can be reasoned. You can reason kind of like a mathematical deduction here. You can use this to reason what happens to a program. And if you can reason this with your pen and pencil and the paper, it means it can also be reasoned automatically. So in dynamic analysis, then we can have different taint policies. We decide in what cases we're going to taint this. For example, this is a data. The data is encrypted. We're going to taint it. The data has been added 5. We're going to taint it. Then the taint can be at different layers. It can be at the source code layer. It can be at the machine code layer. It can be at the register layer. So this one defines all those taint rules. I will use one example to show you. So this is a paper published in 2014 and also 2010. It's an OSDI paper. It's called Taint Droid, Information Flow Tracking System for Privacy Monitoring on Android phones. So this is basically the tool I explained to you just now to find if your applications is stealing your privacy, private data there. And this is a very comprehensive work because Android is a very complicated system. Android, you develop applications in Java. Java runs in the Dalvik virtual machine, but everything runs on top of Linux. So to track the things moving from the Java to the kernel to eventually move out of the phone, there are multiple layers, and they have a very comprehensive work to taint all the layers. Very complicated. That's why they published in OSDI. Let's see. Let's see if I have any results to show you here. So basically, those are the details of the paper. Say they have to tank many different layers: the virtualized, the Dalvik virtual machine, the native system libraries, the kernel, also the file system level, all very complicated. I think I have one. Oh yeah. So let's say this. I'm going to show the result here. So they analyzed hundreds of applications, I believe, in the Android market that time, and try to say if they are really stealing some sensitive information. Let's say applications grouped by requested permissions, location, camera, audio, phone state. And let's say, so those are real application names. The weather channel, you can say BBC News, and they can, so their tool tells you whether those applications were using those permissions, using those sensitive data. The findings were, so this one is more like the requesting of permissions, and this one is how they are actually using those sensitive data. Phone information to, let's say, observe the behaviors is phone information to content server. They find out two apps sending out the phone numbers. IMSI identifies your SIM card. That's the ID of your SIM card. So those supposed to be secret. Those supposed to be personal identifiable information, right? Because your phone, you're not going to change your SIM card very often. So if different apps can track your IMSI, they can link things together. Actually, right? Different apps, they can link things together, know what you're doing. They find two apps are doing that. Seven apps, they are using the device ID to track you, and 15, they are getting your location information and send it to advertisement servers. So those are usually information the apps didn't disclose to you, but their analysis find that. Okay, so the last very useful technique proposed in last 14 years. I think this one probably started when I started doing PhD. I noticed some people have been using this that time. It started with some logic people, because symbolic execution, because names very logic people, the security people brought this idea to security. Symbolic execution is obviously different from our regular expression, regular execution, and the regular execution, we can call it the concrete execution. So we have symbolic execution and we have concrete execution. So in symbolic execution, those values or variables, they are not concrete values. So far we're doing, for example, int a equals 1, and we know a has the value 1. Let's say what 1 is not a concrete number. 1 is not 1. 1 is just a symbol. Okay. Then we can define many different variables as symbols instead of concrete values, and all the calculations on that symbol will not generate concrete values. So previously a equals 1, a plus plus, then a equals 2, right? What if a is just a symbol? A plus 1 will not generate 2 or any concrete number. A plus 1 will only lead to a plus 1, and that's a new expression on a. So the good thing about this is we're not going to have concrete values. Instead, we have symbols, so we can execute on those symbols, and we only concrete it when we need to. Let's say this piece of program, we're getting input from user, and the times 2 that, then x, in this case, we say x is a symbol. Then after that, x is only 2 times something. Then there is a predicate to say if x minus 5 is this, then go to 3, others go to 4. If this is a concrete execution, then let's say if this is fuzzing, what we will do? We will feed many different input here, right? We're going to fuzz it to give it many different input and try to cover both branches. And you can see there are 2 branches here. One is x equals to 19. Another one is everything else. And x could be an integer, 32-bit or 64-bit. So the chance for me to cover both branches is very small, because only one out of 2 to the power of 32 or 2 to the power of 64 will trigger the branch 3, the failure. All other input will trigger the normal behavior. So no matter how fast my fuzzing tools is, I may never be able to trigger this. Very hard to trigger. So how can we trigger that? That's why fuzzing and symbolic execution actually they are used together. So here we use symbolic execution to guide the fuzzing, to guide us to generate better test cases. So what we do is, here we get x is, let's say there is a symbol we call it s. So x will be 2 times s. Then we keep execution, symbolic execution. Then we have the predicate that we know 2 times s minus 5 equals 14 will go to branch 3. Otherwise, it go to branch 4. Then we have a formula here. The formula is 2 times s minus 5 equals 14. That's our formula. Using that formula, we feed it into a mathematical solver to solve this formula. And the solver will tell us, oh, your x needs to be 19. Your input needs to be 9.5. Okay, to trigger the third line of code. Then the fuzzer will say, okay, that will be my next input. My input will be 9.5 instead of just randomly guessing there. Okay, right? So that's why that's one way to generate better test cases faster. So like I said, this is what happens at the start of the program. Let's say the condition, the symbolic condition is nothing there. Then we execute x equals to 2 times get input. Then we know x value is 2 times s. S is a symbol, not a concrete value. We record this mathematical equation there. We keep execution, this one. Then we know the mathematical equation here is 2 times s minus 5 is 14. Then we take this mathematical equation, feed it to a solver. Right now, solver is a relatively mature technique. You give an equation like this, of course, in their own solver's language, you have to encode this. Then you can solve that to tell you, hey, what s concretely should be. Of course, symbolic execution is not perfect. First of all, it can be very slow. Imagine in symbolic execution, because it's not concrete. It's not like you have a control flow graph. You are executing one path of control flow graph. Every time there is a predicate, you need to create a new process. one process executed the left-hand side, one process executed the right-hand side. Then you execute both of them simultaneously. So there will be a path explosion problem. That may make the analysis infeasible, right? Also, there are many other problems as well. That's why there are still much to be done in all of those areas. Okay, so basically that's all I have for today. I hope I gave you a good overview of the more advanced techniques, which we do not cover in this class. And but if you go to research in this area, those are the things you need to know. Next class will be the last one. I'm going to show you guys a video. I think it's a 1 hour video. That's a keynote speech from last year's CCS. And I like that keynote speech a lot because it covers almost everything we talked about in this class. So you can see from a slightly different angle, a lot of professors talking about what we learned in this semester from a different angle, and to help you better understand the problems and also the landscape. Okay, cool. See you Wednesday. Any questions? Good. Okay, and see you guys Wednesday.